We present learning and aggregating lane graphs for urban automated driving. In order to make urban automated driving a reality, HD maps including lane topologies are required. Tasks such as planning as well as forecasting heavily rely on their availability. Nonetheless, the task of lane graph estimation from aerial images remains highly challenging due to complex lane topologies, occlusions, and out-of-distribution scenarios. To this end, in our work, we study the iterative prediction of lane graphs from aerial images and show how multiple lane graphs can be aggregated to a larger, consistent graph in a method-agnostic manner. We draw inspiration from trajectory prediction by selecting a local corridor for which we obtain a directed lane graph first. Next, we traverse our current solution while aggregating in order to populate the graph over time. And finally, we initialize our method from multiple starting poses simultaneously in order to attain global solutions. Our model for successor lane graph prediction takes a small aerial crop as input. We predict center lines in an ego-traversable area in order to sample nodes and edges. Then we use a novel graph neural network termed LaneGNN in order to predict the ego-reachable lane graph. We regularize our method by using a combination of binary cross-entropies regarding node scores, edge scores, as well as classifying nodes whether they are terminal or not. Naturally, the LaneGNN predictions contain a number of redundant paths. We obtain sparse solutions by pruning the graph in a search manner. We obtain all paths towards multiple terminal nodes using Dijkstra's algorithm. In the second stage of our approach, we aggregate local successor graphs into a globally consistent lane graph. We achieve this by selecting an initial virtual agent pose and predicting a successor graph. In the following, we traverse the current graph solution by one edge length per step. Each time, plausible branches of the predicted graph are merged into the aggregated graph and thus extend the aggregated graph if new grounds are covered in the respective crops. Merging two lane graphs is especially hard because arbitrary longitudinal differences of the node positions along a branch can lead to stark errors and distortion when performing Euclidean merging. Therefore, we neglect the longitudinal part and merge the two branches based just on their lateral difference in some local corridor. We leverage multiple mechanisms for maintaining prediction noise, such as removing unvalidated lane splits and mergers, as well as redundant paths. To evaluate our approach on challenging real-world data, we compiled the novel UrbanLaneGraph dataset. It is a first of its kind for large-scale lane graph estimation and contains aerial imagery at 15 cm per pixel for 6 different US cities. The graph annotations cover 5,000 kilometers, which were aggregated from the Argoverse 2 dataset. In addition, we introduce a novel benchmark challenge called the UrbanLaneGraph Benchmark. Along with the raw graph annotations and images, we share pixel-wise map layers of intersection areas, lane center lines, lane directions, and drivable surface. We make the dataset, evaluation code, and API available online under these links. In addition, we host a benchmark challenge on eval.ai with 3 distinct tasks. In the first task, we aim at predicting ego-reachable successor lane graphs from the current pose of the virtual agent. In task number 2, called full lane graph prediction, we evaluate the quality of aggregated lane graphs in the context of HD map estimation. And finally, we carry out high-level path planning on the predicted lane graphs intended to analyze the fidelity of routes planned. Here we show qualitative comparisons of successor graph predictions of LaneGNN and 2 baselines. While LaneGraphNet produces generally low performance compared to the skeletonized regression, LaneGNN exceeds at predicting lane splits while showing high accuracy across both intersections as well as straight road sections. LaneGNN achieves slightly higher graph precision and recall while showing high split point prediction accuracies compared to the skeletonization method. For more insights on the evaluated metrics, please refer to our paper. In task number 2, we perform iterative aggregation of successive LaneGNN predictions, as shown in the video on the left. In addition, we initialize multiple model instances simultaneously in order to cover larger map areas, as shown on the right. Here we visualize full lane graph predictions of lane extraction in the top row and aggregated lane in predictions in the bottom row. Our model is initialized at the shown poses, indicated with yellow circles here. We can see that our approach handles occlusions and out-of-distribution scenarios very well compared to lane extraction. This is further reflected in the quantitative evaluation, where our two-stage approach outperforms lane extraction by a considerable margin. In the bottom, we also show how our lateral aggregation improves the graph quality compared to a naive Euclidean merging scheme shown in the top image. For task number 3, we plan paths on the predicted graphs between random nodes using A-star search. Our approach proves to produce shorter and more direct paths, which coincides with smaller mean distances compared to the ground truth graph, while the success rate is on par. With that, I want to thank you for your attention, and please feel free to check out our paper on arXiv or in Vancouver at CVPR 2023.